Okay, so hopefully you've seen the first video that we did on complex branches, and the next thing I want to talk about are substituents other than alkyl groups. So here we go. One of the non-alkyl groups that we're interested in exploring are the halides. So if I were to name a compound like this, we would follow exactly the same procedure that we've done before with naming simple alkanes, and that is the first step is find the longest continuous carbon chain. So we would do that. Looks like that. So this is also 6, so hexane. And then we would start numbering just as we've done before in a direction such that the two substituents add up to the lowest possible combination. And for halides, the numbering system is the same priority system as alkyl groups. So numbering this from the right shows that I have a fluoro substituent, and notice the spelling. So we have a fluoro substituent, we have a methyl substituent, and the numbering suggests that going 2-fluoro, 3-methyl, which add up to 5, is better than if we'd gone the other way from left to right, which would be a 4-5. 5-fluoro-4, which adds up to 9. So this is relatively straightforward. And again, we put these things in alphabetical order: 2-fluoro, 3-methyl, hexane. Okay, if I'm looking at naming ethers, remember that an ether is a compound that has an oxygen atom in the middle. And so we're going to treat these as alkyl groups that have an oxygen, and those are called alkoxy groups. So what you want to do is, looking at your ether, is find the longest continuous carbon chain that contains the ether. So in this example, if I look on the left side, I have 4 carbons. I look at the right side, I have 3 carbons. And I have this oxygen in the middle. So the 4-carbon wins out, so this is going to be a butane. That's the root. Now we have a 3-carbon branch with an oxygen on the attached, and so remember 3 carbons were propyl branches. And so now if you have an oxygen in the space, you lose the YL and you put an oxy, OXY. So this becomes 1-propoxy butane. I'll just move that over so you can see that it's one word. So 1-propoxy butane. Let's get a little more complicated with ethers. So here we have a compound that has 5 carbons on each side. So if I go here, there's 5 carbons. If I go here, there are 5 carbons. So which one wins? Well, the one that wins is the one with most branches. Okay, so the one that has the most branches wins. So this is a pentane. And it's this now substituent that we can now include the oxygen and the 5 carbons. This is a pentoxy branch. And now we want to number our compounds. And here, the ether gets the low priority. So if you can make that oxygen the lowest number possible, that would be very good. So this is now 2,3-dimethyl. And so M comes before P, so we put this in alphabetical order just like before. So this is 2,3-dimethyl, 1-pentoxy pentane. Hope that's clear. Let's try something more fun. Well, more complicated. So here's 2 cycloalkyl groups on an ether, on an oxygen atom. So again, we find the longest continuous carbon chain. That guy wins. He's got 6 carbons. This guy's got 5. So this would be cyclopentoxy cyclohexane. So that's how you name ethers. Okay, your book also talks about naming nitroalkanes, and so these are compounds that look like this. Remember, the nitro group from nitric acid is a zwitterionic species that actually has some resonance. So just as an aside, we can draw resonance structures on nitro groups. That look like that. You'll often see them just labeled as NO2. So numbering them is the same way as you number any other alkyl group. This would be 2-nitrohexane. And again, you put them in the alphabetical order just like you always would, as you've seen before. So that's the simple nomenclature of ethers, nitro groups, and halides.